this is Dr. Sridhar back to you with another video session on the efficiency calculations and various types of losses in three-phase induction motor. Now in today's video session, I am going to discuss about various types of losses occurs in three-phase induction motor, and with the help of these losses, how that efficiency can be computed. Various power flow diagrams also we are going to discuss as a part of today's video session. So broadly, if we are speaking, this losses occurs in the three-phase induction motors can be classified into two broad areas. As we know that the components are, some of them are fixed and some of them are variable. So based on this, the losses could be classified into two categories: variable losses and constant losses. Now first, if you are talking about the constant or fixed losses, again these constant or fixed losses can be classified into three more categories. Those are iron or core losses, and mechanical losses. Those are nothing but sometimes in addition to that, or some of the cases, this brush and frictional losses are also considered as a part of mechanical losses. So these are the constant or fixed losses. Coming to the definition, what type of losses can be called as constant losses or fixed losses means irrespective of the loading conditions, whether if you are talking about from no load to full loads, from no load to fully maximum amount of load, if the losses remains constant, such losses are called as the fixed losses or constant losses. Now again there are various classes, like suppose if iron losses or core losses. What exactly iron loss and what core loss is? These iron losses or core losses again classified into two more categories. Those are hysteresis losses and eddy current losses. So about hysteresis and eddy current losses, we have discussed so many times, and what are the parameters highly influence hysteresis loss and eddy current losses, what is a mathematical expression, and this hysteresis and eddy current losses depends on what parameters. Suppose how these losses can be reduced or limited within the acceptable limits. All these things we have discussed in our previous videos as a part of the transformers or as a part of DC machines, etc. Even though again I am going to touch some of the basic points which highly requires for better understanding of these losses as a part of three-phase induction motor. Now in hysteresis losses, these losses can be minimized by using high-grade silicon steel. Now these losses mainly depends on the thickness and frequency of operation and supplied voltage and magnetic field density. So these are the various parameters highly influences these core losses. Now eddy current losses, these are minimized by using lamination of the core. Now if the lamination could be done, then the total core is going to divide into various pieces. Now that area of cross section reduces, means the current has to flow through some segment of area, that is a laminated area. If the area of cross section reduces, then proportionally the resistance it will be increased. If the resistance increases, for the small amount of eddy currents, the maximum amount of opposition it will be offered by that laminated segment. So in these cases, what happens that losses or the flow of current, it will be ceased to a very, very lower value. Now this is how we are going to reduce the eddy currents, so that proportionally the eddy current losses can also be minimized. And one more important point is the core losses depend upon the frequency. As we just now we have discussed that the core losses depends on the frequency. Now these core losses also happens in the starter and it also happens in the rotor. Now in the starter, if you are talking about the core losses in the starter segment, the losses are considerable. Why? Because the core losses in the starter frame is directly proportional to the frequency. Frequency is the supply frequency, which is equal to 50 Hz. So okay, considerably that losses are it has some finite value. But whereas in the rotor, now in the rotor, the operating frequency of the rotor is very, very small, that is slip times the supply frequency. So suppose if you are taking a 50 Hz AC input, if you are giving to the starter frame, now almost about 1.5 Hz become the frequency of induced voltages currents in the rotor segment. So almost about the slip of 3%. So 1.5 Hz as compared to 50 Hz is nothing. So in the rotor also core losses will happen, but as compared to the starter core losses, rotor core losses can be eliminated. This is the one of the important point we had to remember as a part of eddy current losses. Hence, the rotor core loss is very small as compared to the starter core loss and is usually neglected in running conditions. And one more category is mechanical and brush friction losses. As I told just now that mechanical losses and brush and friction losses, air windage losses all comes under one category. Those are nothing but the mechanical losses. Mechanical losses occur at the bearing and brush friction loss occurs in wound rotor induction motor. So what is that wound rotor? Because wound rotor induction motor is nothing but it is a slip ring induction motor. In the slip ring induction motor, variably by connecting some external resistances or rheostats, you can control the torque or you can control the rotor currents. So in that cases, in order to coordinate with the external circuit connected to the rotor circuit, now you have to connect brushes and wearing and tearing is also very, very important. So this wearing and tearing of the brushes along with the bearing support, mechanical support, sometimes losses will be predominantly plays vital role. Especially this is very important, you cannot ignore these mechanical losses whenever we are talking about the slip ring induction motor. But in the squirrel cage induction motor, these losses are almost constant and very small also. Because you cannot operate or you cannot regulate the torque or starting currents by connecting any external devices in the squirrel cage induction motor. These losses are zero at start and with increase in the speed, these losses increases. Yes. If the speed of the motor goes on increasing, so air maybe blows in the opposite direction. So air friction and windage losses will play a vital role. So that's why if the rotor of that three-phase induction motor is going on peaking the speed, then the opposition will be also increases proportionally. So those at that particular instant, these mechanical losses are predominantly high. These losses almost remains constant in the three-phase induction motor. The speed usually remains constant. So as compared to the synchronous mode and very close to the synchronous speed, this three-phase induction motor is operating. So these mechanical losses more or less can be treated as a constant losses because that rotor is always behind the synchronous speed. So the difference is nothing but the slip speed. So that slip speed is very small. So in view of this, as the losses are also influenced by the speed, and if the speed is very nil, the difference between the rotor speed and the synchronous speed is close to zero, in such cases, these losses can be treated as a constant losses. So these are the various losses as a part of the constant losses we can describe. So one of the important one, variable loss. So what are the variable loss? First, let us talk about various power flow diagrams. So first, we used to give some electrical inputs, three-phase electrical input to the starter frame. And in the starter, what happens? There may be some starter copper losses and starter core losses, starter iron losses and starter copper losses. Because that is the frame through which we are going to inject that electrical input to the three-phase induction motor. So here, we cannot ignore the starter copper losses because it is going to carry the supply current. And we cannot ignore the starter core losses because core loss is a function of frequency. Frequency is 50 Hz, so it is a considerably high. So starter core losses cannot be ignored. So both the copper losses and core losses in the starter frame are very, very important. And after meeting the starter core losses and copper losses, the remaining electrical input power, it will be flows into the air gap. So this power is also called as air gap power, or that will be the input for the rotor. So how much of rotor input power means electrical input minus starter losses. What are the starter losses? Starter core losses and starter copper losses. Then the remaining power will be the input for the rotor. Sometimes this input to the rotor can also be called as air gap power. Then again, input to the rotor, it will goes to the, now in the rotor frame, especially if you are talking, now there are some losses. What are the losses? Rotor losses. What could be the rotor losses? Now there may be rotor copper loss and there may be rotor core loss. Now here, rotor is a segment where that induced EMF or currents associated with the rotor circuit will be operating at very, very lower frequencies. That is nothing but the slip times the supply frequency. So for a 50 Hz electrical machine, the rotor induced EMF or currents are just 1.5 times or 1.5 hertz. So as compared to 50 hertz, 1.5 hertz is very small. So in view of this rotor core losses can be ignored as compared to the starter core losses. But rotor copper losses are nothing but those are the losses occurs in the machine because of the flow of rotor current. The rotor current is the current, it is also the load current. So if the load proportionally changes, proportionally rotor currents also changes. If the rotor current is considerably large in the magnitude, so rotor copper losses cannot be ignored. Only rotor core losses can be ignored because the operating frequency is very, very small. But if you are talking about the rotor currents, it is very large. So that's why rotor copper losses cannot be ignored. That's why we are more specifically we are mentioning that rotor input is going to meet the rotor copper losses. Then the remaining power will be appeared across the rotor output terminals as mechanical power developed. So that will be the mechanical power developed across the rotor terminal. That will be the input to the shaft. Then again, now how this rotor output will be conveyed to the external circuit. So how this rotor output power, that is the gross mechanical power developed by the rotor, how it will be communicated to the external load circuit. That is nothing but the utilized power. So that is the power actually we require, and we are going to collect it from the shaft terminals. So that output of the three-phase induction motor is also called as the utilization power of the three-phase induction motor. It is also called as the gross output power, completely motor output power. So what is the difference between gross mechanical power developed across the rotor and the shaft power means? Again, there are some mechanical losses are there. So gross mechanical power developed by the rotor, it has to meet some mechanical losses. Those losses are nothing but the air friction and windage losses. Once these losses met properly, then the remaining power will be available across the shaft. So these are like this, we can classify or we can discuss various power stages along with the various losses, how this electrical input power goes on converting. Now motor input, how much, suppose let us say root 3 into VL into IL cos pi, if you are giving it as at the input terminals for the three-phase induction motor. So some portion of this after meeting the starter losses, it will be given to the rotor, that is through the air gap. Then again the rotor input power after meeting some rotor copper losses, it will be available across the rotor output terminals. Again after meeting some mechanical losses, the rotor output power, some portion of the rotor output power will be communicated to the shaft. So these are the various power stages, and at every stage predominantly we have mentioned what type of losses we had to consider in order to calculate the efficiency also. These losses occur. Now variable losses occur due to the current flowing in the starter and rotor windings. Just now also we have discussed about this. As the load changes, the current flowing in rotor and starter winding also changes, and hence these losses also changes. So one should not ignore the copper losses at any point. But based on the frequency or based on the other parameters, sometimes these core losses can be ignored because those losses are nothing but the constant in the magnitude. But whereas variable losses are not constant, these are nothing but the fluctuating. These will be varied with respect to the load. So again, let us try to derive the efficiency expression for the three-phase induction motor. Now, normally this is a three-phase induction motor. So electrical power induction motor is nothing but it is a converting device of three-phase electrical energy to the mechanical output power. So three-phase electrical energy we had to give to the induction motor. So that will be given to the starter frame in the three-phase manner, that is red, yellow, B or ABC. Like this three-phase input power, it will be given to the starter frame, that is various three phases. Normally it may be connected in the star or sometimes it may be connected in the delta based on the applications. So let P input is nothing but electrical power supplied to the starter of three-phase induction motor, and VL is nothing but the line voltage supplied to the starter, and IL is nothing but the line current that will be there in the starter windings, and cos pi is nothing but the power factor of three-phase induction motor. So electrical power input to the starter is nothing but the P input. What is the formula for this? That is root 3 times of line voltage, line current into power factor. So we have mentioned here. So a part of this power input, now this is the total electrical power we are giving to the total three-phase induction motor. More exactly if we are speaking to the starter frame. So some of them it will be utilized to meet the losses, or some of them it will be converted into the losses. Remaining power it will be goes to the rotor as an input. That's what we are mentioning here. The remaining power after starter losses, the remaining power, it will be supplied to the rotor as rotor input. So the rotor input, generally it is represented with P2 is equal P input. P input is root 3 BL into IL into cos pi minus starter losses. Those starter losses here, both the losses we have to consider, starter copper losses and starter iron losses. So here finally we have given some amount of input power to the rotor. Now after receiving that input power, what the rotor will do and what are the losses that rotor input power has to meet. The rotor has to convert this rotor input into mechanical energy, but this complete input cannot be converted into the mechanical output as it has to meet rotor copper losses. After meeting this rotor copper losses, out of the input to the rotor, P2 minus rotor copper losses will be the gross mechanical power available or developed by the rotor, and that will be available across the rotor terminals. After supplying the rotor copper losses, the remaining part of the rotor input P2 is converted into mechanical power, that is gross mechanical power, that is represented with P suffix small m. Let Pc be the rotor copper losses. Suppose if you are assuming P suffix C is the rotor copper losses and I2 is the rotor current with respect to the load under running condition, R2 is the rotor resistance per phase, then Pm is the gross mechanical power developed, then the copper losses, rotor copper losses Pc is equal, there are 3 phases are there, so that's why 3 times of I2 square into R2. Then what could be the gross mechanical power? Gross mechanical power is the output power or mechanical output power that will be available across the rotor only, not across the shaft. That is a very, very important thing. So gross mechanical power is nothing but Pm is equal rotor input minus rotor copper losses, P2 minus Pc. Then this mechanical power developed is given to the load by the shaft, but there occurs some mechanical losses like friction and windage losses. So totally total output power of the 3-phase induction motor is nothing but gross mechanical power output developed minus mechanical losses. So P output is directly finally that will be the shaft power or useful power we are going to extract from the 3-phase induction motor. So P input is, it will be the input for the 3-phase induction motor. P out is nothing but this is the shaft power or useful power. We are going to get it from the 3-phase induction motor. So in this process, in this session, we can easily understand how that electrical input power is flowing through various stages and meeting various losses, compensating various losses, and how this electrical nature is converting into the proportional mechanical power. We can discuss everything. Now, finally, what is the efficiency? Efficiency is defined as the ratio of the output to the input power. So, efficiency is nothing but the output power to the input power. So, here also across every component, now across shaft also or across rotor, across starter, at everywhere you can easily calculate the efficiency if it is asked. Suppose if you are taking rotor efficiency, what is the rotor input? Rotor input is nothing but the air gap power or starter output power or rotor input power. Rotor input power we have represented with P2, and rotor output is nothing but the gross mechanical power developed by the rotor. So rotor efficiency is nothing but Pm by P2, that is nothing but the rotor output to the rotor input. So gross mechanical power developed by our rotor input, that is nothing but Pm by P2, that is nothing but the rotor efficiency. So finally 3-phase induction motor efficiency is nothing but power developed at the shaft, that is nothing but the P out to the electrical input to the motor, that is nothing but the P in. So this is the various losses the induction motor will have whenever you are applying some electrical input as the input source to the starter frame, and how it will be converted into the mechanical power, and what are the various losses that 3-phase induction motor will have, and how that efficiency of the 3-phase induction motor can be calculated. So I hope these losses and these concepts are very clear to everybody, and in the next session we are going to discuss about various problems associated with efficiency calculations. Thank you for watching this video. Thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.